Now that we know how to determine the direction that forces act, we can finally talk about the most important equation in this class. And we can start doing applications. Most important equation in this class. And that equation is Newton's second law. And Newton's second law says F net is equal to the mass of an object times its acceleration. This F net, what we're talking about here, is the sum of all the forces acting on a chosen object. M is the mass of the object. And acceleration, A is the acceleration of the object. Well, later on when we start talking about rigid bodies, we'll see that if a body has dimensions, if it has lengths in different directions, the acceleration of every point on the body can be different. And so this doesn't really matter to us now that we're thinking of everything happening at a single point. We're not thinking about bodies rotating and stuff like that. But we will see that this acceleration has to refer to the acceleration of the center of mass of the object. Okay, so that's just sort of for later. But this is the number one most equation in this whole class. It relates the forces acting on a body to the motion of the body. And we're going to start out by talking about, so this part one that we're doing. Is when everything is along a line. Okay, so later we're going to get to problems where you have to use some trigonometry and stuff, but we're going to start out with ones where you don't have to do any trigonometry. And so we can just jump into how this works. So I'll start with an example. Let's say that we have a cart that rolls along the ground. The mass of the cart is 20 kilograms. There's a 50 Newton force going this way, an 80 Newton force going this way, and we want to calculate the acceleration of this object. And so you can see that, the 50 Newton and 80 Newton forces are acting along a horizontal line. The motion of this body can only be along a horizontal line. We're going to see that there are some forces that are not horizontal, but those don't affect the problem. So the key thing here is that we just don't have to use any trigonometry in this problem. I'm going to just first choose a positive direction. Let me do that in a different color. So I'm going to say the positive direction is that way. Anything that's moving to the right, I'm going to call positive. Anything moving to the left, I'm going to call negative. And I'm going to start out with a free body diagram. And you always need to start out with a free body diagram. And we're going to use the rules that we talked about in the free body diagram lecture. So here's my outline of the body. You don't have to be careful about the outline, but I'm just trying to be clear as I draw this stuff, what I'm talking about. And what forces are acting? There's a weight force down. That's 20 times 9.8, so 19.6. There's a pushing force from the ground that's perpendicular to the surface toward the body, and I'll call that N. And then there's the 50 Newton force this way, and the 80 Newton force this way. Since the motion of this body is going to be horizontal, anything that's perpendicular to that horizontal line, we're going to leave out of Newton's second law. So we're only concerned with the forces that are acting in, along the line of motion. So these two are perpendicular to the motion. And so we're not going to have to think about those. And so we'll just go straight to Newton's second law. I'll abbreviate that. Newton's second law, N2L. We have the 50 in the positive direction, the 80 in the negative direction, so that's negative. And that's equal to the mass times the acceleration. We get negative 30 is equal to 20a. Divide both sides by 20 and you get that a is equal to negative 1.5 meters per second squared. Since that's negative, we know that that acceleration is in what we defined as the negative direction. That's to the left. And so our acceleration is in this direction with a magnitude of 1.5 meters per second squared. We can also use this for problems where we have multiple bodies in contact. So here's an example of how to do multiple bodies in contact. So let's say that this time, okay, we have one cart over here, and this one is 10 kilograms mass. And one cart here. And this one is 15 kilograms. And let's say there's a 40 Newton force over here and a 20 Newton force over here. And we want to calculate the acceleration. And notice that these two things are in contact, so their accelerations are going to be the same. So when I say what's the acceleration, this is a case where calculating the acceleration of one is the same as calculating the acceleration of the other one. And then second, we want to calculate the force on one of these by the other. That's a pretty common thing. So what's the force on the 10 kilogram by the 15 kilogram? And we're going to do problems like this always in 2 steps. Step 1 is we're going to isolate the whole system. So our chosen object is going to be both of these two together. And we're going to do this in order to calculate the acceleration. And then step 2 is then we're going to isolate one of these two objects. Isolate a single one of these objects. To calculate that contact force. Okay, so the first step is I'm going to draw a free body diagram of the whole system. So there's the two carts together. The weight is 25 times 9.8. So that comes out to be 245 newtons. And then there's a pushing force from the ground onto the 10 kilogram body. So I'm going to call that N10. And then another different pushing force from the ground onto this one, I'll call that N15. And then there are the two forces that were given. There's a 20 Newton force going this way and a 40 Newton force going this way. And like before, I just need to be clear to myself. You don't have to write this if you don't want, but you have to be clear about what you're calling the positive direction and negative direction, and that's your choice. On these horizontal ones, I always choose the positive direction going to the right and the negative going to the left, but you could do it the other way and it would work out the same. And so now we want to calculate the acceleration. The motion, the acceleration, and velocity and position and whatever is only going to change horizontally. And so these three forces that are perpendicular to that motion, we can ignore. So our Newton's second law is only going to deal with the horizontal stuff. So Newton's second law says the 20 is in the positive direction that I chose. The 40 is in the negative direction. And all that is equal to 25 times the acceleration. And so we get negative 20 is equal to 25a. And so a is equal to negative 0.8 meters per second squared. And what that negative means is that the acceleration is in our negative direction. So you can think of this as an acceleration with a magnitude of 0.8 in that negative direction that we chose. Okay, this time we're not done with this problem yet. The next thing we have to do, we're trying to calculate the force on the 10 by the 15. We're trying to calculate a force on the 10. So I'm going to isolate the 10. So free body diagram of the 10 kilogram body. And there's a weight force of 10 times 9.8, so that's 98 newtons down. There's the pushing force up of N10. And then if you look at the problem, on the 10, there's the 20 Newton force, but the 40 doesn't act on it. That's acting on something else. We're just looking for these contact forces that are acting on the boundary of the one that we've chosen, the 10 in this case. So we do have the 20. We don't have the 40, but what we do have on the right side of the 10 kilogram body is a pushing force from the 15 kilogram body. And so the rule says for pushing forces, it's perpendicular to the surface toward the chosen body. And this is the one we're trying to calculate. And so I'll just give that a variable name. Normally I call that R for reaction force. And now go to Newton's second law. We're going to ignore these two because they're perpendicular to the motion. And we have that 20 minus R is equal to the mass of the chosen body times the acceleration. Well, now you see the reason that we isolated the whole system and calculated the acceleration first. If we went into this equation and didn't know A, we'd have two variables in here. But now that we know A, we can plug that in because both of these two bodies have the same acceleration. And we get that 20 minus R is equal to negative 8.0. And so R is equal to 28 newtons. And now what about the direction? Well, you have to be a little careful because this says positive. So your first thought might be, okay, this is in the positive direction. But notice in our free body diagram, we specified what a positive value of R would mean. In this case, a positive would mean to the left, a positive value of this variable. And so you have to go based on the arrow that you drew in the free body diagram. And so what we have here is a force vector to the left of 28 newtons. Now, the last way that we're going to apply this kind of problem is when there are pulleys involved. So this is when we have cables and the cables go over pulleys. And all a pulley can do, all a pulley ever does, is change the direction of a force. So this is an example of a cable passing through pulleys. And the key thing is pulleys only change the direction of a force. Okay, so I'm going to show you how to do a problem like this. So let's say that we have this ledge, and there's a pulley at the corner. And on the horizontal surface, we have a cart. I'm going to say that's 5 kilograms. And a pulley, a cable that passes over this pulley, and then hanging from the other side of the cable is a 2 kilogram mass. And so we're going to ignore the forces that the pulley applies to the cable, and instead we're just going to think about this as if it was all hanging. Either it's your choice. You can think about whether you want to rotate what's happening to the 5 so that it's all acting vertically, or you can think of the 2 kilogram one as rotated and all of it acting horizontally. I guess I'm going to do it all horizontally. If the question ever asks for, say, what's the acceleration of the 2 kilogram or, the other body in the problem, then you want to keep that one in its orientation and rotate the other one. But what I'm going to do is just, on these problems, just always think of the problem as everything happening in a line. That means you're going to rotate the body, and you're also going to rotate all the forces. And I think when I do it, it'll make more sense than me just trying to talk about it. So I'm going to start, let me make the problem first. So let's say we want to calculate the acceleration of the system. And second, we want to calculate the tension in the cable. Okay, so the way I'm going to do this problem, and I'm going to think of my positive again going this way and my negative going this way. And I'm going to rotate the cable and the 2 kilogram mass and all its forces. You can think of rotating it 90 degrees clockwise. And I'm going to draw my free body diagram like this. I have my cart over here, and my cable connecting the two bodies. And then I have my 2 kilogram mass. This is the whole system. And since I rotated that 2 kilogram mass 90 degrees clockwise, that downward weight force is also going to be rotated 90 degrees clockwise. So, and you can see, like, another way to think of it is you're thinking of all the forces. Are they in the direction of motion, or are they perpendicular to the direction of motion? That weight force is in the direction of motion of this 2 kilogram body. And so this free body diagram, our direction of motion is horizontal, so that weight force has to be horizontal. So this is 19.6 newtons that way. That's the weight on the 2 kilogram. And then on this body, we have a weight down. That's 49 newtons. And we have a pushing force from the ground. I'll call that N. And now that's everything. The one thing we are ignoring is that pulley is applying a pushing force to the cable. But we're just ignoring that completely and just knowing that all a pulley does is change the direction of the cable forces and the direction of the motion of this system. So this is the way we're going to treat that. So now go to Newton's second law. And we have negative 19.6. That's in the negative direction. These two are both perpendicular to the motion, so those don't show up. And this is equal to the mass of the system. The system is 7 kilograms times the acceleration. And you get that A is equal to negative 2.8 meters per second squared. And so the negative means that that cart is accelerating this way at 2.8 meters per second squared. Okay, which means that that hanging mass has to be accelerating down because this thing is moving as a system. And now we want to calculate the cable tension. So first we isolated the whole system, and now we're going to isolate one of these two bodies. And you might as well do the one with the least going on. So I'm going to isolate the hanging mass, and I'm going to keep that rotated orientation so that there's no contradiction in any signs that we're using. So the forces acting on this are a 19.6 newtons to the left, and then the other force along the direction of motion of this is a cable force. That's a pulling force. So it's parallel to the cable away from the body. In this orientation, it would be up. After the orientation, it's this way. And so Newton's second law says negative 19.6 plus T is equal to 2 kilograms times the acceleration of negative 2.8. And so we have negative 19.6 plus T is equal to negative 5.6. And so T is equal to positive 14.0 newtons. So what that says is if you had a system like this and you didn't want that cable to break, you would have to choose a cable that was strong enough to at least handle a tension of 14 newtons. Instead of isolating the 2 kilogram cart, the 2 kilogram mass, I isolated the 5 kilogram cart. It would have worked the exact same way, and we would have gotten the same exact answer.